All right. Can we do a sound check in the chat? Normally you hear the music, but you should also hear my mic. Perfect. So the webcam should be a bit crappy because it's an experimental setup with a webcam over the Wi-Fi, but for the rest should be okay. Alright, maybe tell me in the chat where you are coming from. So there's Rainer from Germany. Altex, you're living in the UK if I recall. Yeah, London. Do you have people from other continent where it's not evening there? Okay, so I think I will start now. Screen with cam. Yeah. So the goal of today is not to have the full reinforcement learning. Oh, St. Petersburg in Russia from Kirill. Oh, nice. What time is it in Russia now? Quite late, I assume. So the goal for today is to have to set up the simulator, even though probably some of you already know how to do that, and then plug it some reinforcement learning and then start doing some reinforcement learning training. So this is the first session. In another series, I would like to dig more into how to make the process faster, how to make it smoother, and how to make it work better. But we will start with the simple things. And in fact, with out-of-the-box training, you can get already okay agent. The main part will be how to extract information from the camera. But let's not go ahead and let's kill the current reinforcement learning agent. So the first thing first, of course, if you want to use the DonkeyCar simulator, you can look for DonkeyCar gem and go on Ton Kramer repo. And if you go in the releases, there's different binaries. So I will be mainly using Linux, of course, because that's the easiest. And all you need to do then is go to the assets, download the binary, which is corresponding to your OS. And once you have downloaded that for Linux, you need to actually activate it as executable. So once you have done that, so it's in the Gym DonkeyCar. Let me go back to it. Once you have done that, when you open the simulator, so you have the simulator, you have the different ports, one port for communicating with the simulator, one port for private API, and then some time scale, for instance, for running the simulation faster, and then you can activate different options. And we're going to leave then mostly to default. And then you have different environment, different circuit that you can take. And if we want just to drive on it, then we can click on pace car, manual driving, go save, and for instance, go on the mountain track. And then here we can start driving. So the DonkeyCar simulator, it's mainly that. You have a car, you have a camera on the car. You can drive it by changing the steering and the throttle. And you may have additional sensors like LiDAR or the GPS position, and also the speed or accelerometer. So this is for the simulator. And the next things we're gonna do is actually create, so download this Git repository, which will be, in fact, it's the interface to interact with the simulator. And so for that, let me open it on the side. We're just going to create, is the terminal big enough, by the way? We're just going to create so a new folder. Let's call it Donkey. And in Donkey, we're just gonna clone this repo. Okay, so in this repository you have different things, and the main in the core you have everything which is related to creating a socket client with a simulator. I think it's sim client, so it will handle the connection with a simulator. It does all the low-level job, and then in the environment, that's where we will define in fact different things, including the reward function, what do we give to our agent, and also the termination condition. So once we have done that, we go inside the repo, and so I'm currently using a Conda environment, and for this environment I've already installed PyTorch. If you didn't install PyTorch, you can go to PyTorch, go to the getting started, and follow the instructions. And once you have done that, so here there's a setup.py which will allow us to install it, and it requires some basic dependencies. So Gym, which is the interface for the environment, for interacting with, for managing interaction between robots and the environment. NumPy and Pillow. Pillow is for image reading. And to install it, we can just do a pip install -e dot. So -e is interactive because we are going to modify the source code, and we still want the package to be installed. And to check that it's properly installed, we're just gonna go into another folder, open interactive shell, and try to import the package directly. So here we have Gym DonkeyCar, and if we import Gym, if we take a look at here, one folder above, at the init here, there are different environments that are already predefined, which corresponds to the different track that you can play with. And for instance, today we're going to play with a mountain track. So first thing that you need to do is actually launch the simulator. And once you have launched the simulator, then the simplest way to connect to the simulator is just to do a gym.make, then the ID of the environment. And here we go. We have a DonkeyCar connected to the environment. I'm going to also import OpenCV for some visualization. And what we can do is we can just reset our car and just see what our car is seeing. So all the camera config is by default, but we can actually change that, change the camera, change what we see, and the rest. And let's see. So if we do here, I'm just going to show this image. Init test and cv2.waitKey of 0. And here, well, here there's a BGR RGB issue, which is in fact something you get with OpenCV. So to have the proper color, you just invert the channel. So the very last, you keep the width and height, and you invert the color channel to go from BGR to RGB. and then we can take a look at the image, and it didn't work somehow, but so this is what you get from the camera. It is a bit distorted. It is, I think, 100/660, and this is the main information that we will have for the car. Then if you want to interact with the car, as it follows Gym interface, let's do it again. What you can do, so what you can do is directly send commands. You will be able to send the throttle and to send, so again we will just reset our environment, and then when we step in the simulation, what we will get a new observation, we will get some reward, we will get a termination, and then we will get additional information. And so we're just going to call step, and step takes 2 arguments. One argument will be the steering, and the other one will be the throttle. So if we step with 0, 0, it will just do nothing. But we will get a new observation with that shape. So with an RGB observation, we will get some reward. Currently the reward is calculated with respect to the center line of the track. And then if the episode is over, which is false, and then we will have additional information. And in those information, we have the 3D pose of the car, we have the cross-tracked error, so the distance to the middle of the track, we have the current speed, which is in fact a very important information we're going to keep. And then we have some gyro information, acceleration information, and the 3D velocity. I think this is a color, I'm not sure of what it is, and hit is telling you if the car has hit something or not. And let's try to make it move. So to make it move, let's put the throttle to 1, and here we go. And here it starts, and if we want to stop it, then we can just put the throttle to 0 again. So this is the very basics to interact with the car. Okay, car is the direction of the car. Thanks, I'll take. So this is a very basic to interact with the car, and if, I don't know, we crash or something, we can just call reset. Also here in the terminal, what you see is there's some events happening when we cross the start of the line, which will allow us, in fact, to also calculate the lap time. So currently it doesn't make a difference if we did a full lap or if we just cross a lap backward. So that's why we get some weird time here. But this will be useful once the agent is actually doing something interesting. Okay, so far so good. Any question? So the next steps. So here we have set up the basic, very basic. So just downloaded the simulator and downloaded the interface to interact with the simulator. And this interface will allow us to plug a reinforcement learning agent. And I see there are more people, so please, for the newcomers, please tell us of where you are from and maybe what time is it in your zone. Okay, so no question apparently in the chat. So we are going to continue. So what we have done so far is just the very basic, installing everything and making sure we can actually work. And in fact, when we want to exit the simulation, there's a close function that you can call. And here we go. So next things we're going to do is actually take a look at what is currently in the environment, and then we're going to plug that environment with some reinforcement learning agent and do some training. So first thing first, let's take a look at what's inside in practice. if you go to Gym DonkeyCar, I will probably also leave the URL here and on top for people who wants to follow afterward. So I'm in that repo, inside that repo. It's going to be tough. Okay, so I'm inside that repo, and if I go in environment, and I will open DonkeyEnv and DonkeySim. So DonkeyEnv is in fact, let me zoom in, if I can zoom in, will be responsible for providing the interface to the environment, and DonkeySim will be responsible for interacting with the simulator. And okay. Okay, is it still working? So what is in the environment in that case? So the environment is what the agent, so the robot, will interact with. So here the environment includes in fact the robot and the car and the simulator. So the main component in fact of an environment, and that's what we're going to see, is the observation space. So what do you receive as input? Here it's the camera for now, and the action space, which is steering and throttle, and then the environment is everything that will take those inputs from the robot and then do some computation, and then as output will provide new information to the robot. If that answers your question, Altex. Okay, perfect. So the different things I would like to take a look at is what can we configure in this environment. So there's different things that we can configure. We can configure the maximum cross-track error. So above that threshold, your car will the episode, the trial will terminate, and your car will reset. Frame skip is a parameter telling you how often do you, how many times you will repeat the same action sent to the server. This can be useful if the control frequency is too high, then the learning will take too much time. And then you can adjust the camera resolution and define the logging level, and also update the port of the simulation and on which hosts you are communicating with. For instance, if you are doing a race, then you will change that host. Okay, and the first thing we're going to change, so here are the different limits. So what is the minimum throttle that we allow, what is the maximum throttle allowed, and what is the minimum steering and left steering. So this gives you full capability on the car, but there's one problem with that, which is if you let it like that, the car will wiggle around a lot, because this space is in fact quite big, and you don't need that to achieve good time on most tracks. So we're going just to have everything. So instead of having the full steering possibility, we're going to just use half the space, and this will make the learning much faster, in fact, and smoother, because you will force the agent to only use part of the steering. The other thing is, the proper way of doing it would be, in fact, here not to change the value here and to change it afterward inside the environment. But we're going to use an algorithm that doesn't care about that, but that can be an issue. So if your limits are not between -1 and 1 for the action, that can be an issue if your algorithm is relying on the probability distribution, which is, for instance, a Gaussian center around 0. You may get problems, so I did a full video on that. You can search for reinforcement learning visual school, and I did a whole video about how to properly choose the boundaries. And then those boundaries, you can actually resize them inside the environment. So you expose always the same thing to the agent, but inside the environment you do something else. And the other thing we can check is how do we define the observation space. So the observation space is just the pixels. So here we get the sensor size, which is in fact the resolution of the camera, so RGB image. And we say that we have valued between 0 and 255. Then here it's what's happening in the step. So it's mostly just communicating with the simulator, and then getting a new image, and then sending the result to the agent. What I would like to take a look right now, in fact, is inside the Donkey simulator. If you go down and you go to compute reward, compute reward. It's calc reward here. If you go to calc reward, so this is how it is currently defined, the current task. So if it is terminated, it will get a punishment. If you are above the maximum cross-track error, it will also be punished. And if you hit something, it will also be punished. And then, in case none of the termination conditions here are effective, the agent is rewarded to be close to the center of the track while working at full speed. That's it. And below, it's an interesting part. It's when you communicate with the server, you will receive some information, and here it's how you get all the different information that are stored inside this object. So this is a basic reward. It's working okay, as long as being close to the center is a good racing line, which is not always the case. But for today, we're going to stick to that one, and in fact, we can go below a lap of 20 seconds when I did my test with just that reward function. The other thing I would like to take a look at, which is always important, is taking a look at the termination condition. And this is also something that we can change in the future. So currently, if we are above the maximum track error, then we consider the episode to be over. If we hit something, then we're going to also consider the episode over, and then there are other things that are no more available in this simulator, but that were available in previous version, where we had checkpoint or where we had a disqualified flag. So the current main two are if we hit something or if we are above maximum track error. And the other one we're going to add, a termination condition, will be if we are above a timeout, because if the agent runs forever, then it may be also a problem. But we're not going to do that yet. So now the next step for us will be to actually plug in a reinforcement learning agent to the simulation. And for that, we're going to use Stable Baseline 3, which is the library I'm actually developing. So Stable Baseline 3 is a set of reliable reinforcement learning implementations with a nice interface, so you can take a look at the documentation. But basically, all you need to do is import the algorithm, instantiate your environment, and then you can directly play with it. And we can do that right now, in fact. So we have our simulator. We open a terminal anywhere. And then, first thing first for you would be, in fact, to do a pip install stable baseline 3. Today there was a new release, the version 1.4.0. And once you have installed that, then we can start playing with it. So again, we're going to import Jim. We're going to import Jim DonkeyCar. And we're going to import, so here, just to make it fast and not blow up also my RAM, I'm going to import a PPO, even though at the end PPO is not very sample efficient, so this is not the algorithm we're going to use. And once we have done that, we can again instantiate the environment doing gym.make and then the name of the environment. Here it's a Donkey Mountain Track version 0. And here we will have our agent, our robot, which is now in the simulator. Next things we need to do is actually set up our agent. And here we can just set up a CNN policy, so a convolutional neural network policy, because the input is an image. And for that, it's good to use a CNN. Then we pass the environment as second argument, and then we can change some hyperparameters. I'm not going to change anything. I'm just going to set the verbose flag, so there will be some output in the terminal. And what we can do also is just use the untrained agent and see what it is doing. Normally it won't do something, nothing really satisfying, but it's just to show how it works. So what we're going to get is use the model.predict to actually select an action from the observation we get from the environment. And we are going to use also the deterministic flag, because at the end when you want to deterministic to use your robot, you want to have a deterministic controller. You don't want a controller that is exploring. Okay, and next step is just to step into the environment and retrieve the different info. So just step, and we step using the action from the reinforcement learning agent. And if the episode is over, then we can just reset our environment. So here it's just to demonstrate how it will work, how the interface work with the agent. And it's an untrained agent, so it's going to do random things, and it will crash pretty early. Actually, yeah, because it's uninitialized, it will output very small values, and that's what you're seeing here. It's outputting very small values and not doing much. One thing we can do, because we don't want to wait, is go to the timescale, set it to 4, so we have a faster simulation, and go back to the mountain track, and so it will go much faster. Well, much faster here, not much, because it's untrained agent, but at least we have step faster. And we can again reset our environment to reset to the starting pose. Next things we can do is actually start learning on it. So it won't learn anything useful, but I just want to demonstrate the API. So once you have defined your model and you have defined your environment, you can directly ask the agent to learn for a budget for here of 10,000 steps. So here the control frequency is 20 Hertz, so 10,000 steps will be probably 5 minutes or something, but I'm going to kill it before. Yeah, the frequency of the steps, you can choose it, but it is capped to 20 Hertz by the simulator. By the way, if you have any question, please ask them in the chat, as people are doing it right now. And here, so I'm just calling learn, and it starts exploring randomly. It won't do anything useful until very long, because PPO so is very sample inefficient. So what you will see, it will explore randomly and then hit some wall or something. And in fact, maybe I should change that. the default update frequency, so the number of steps the algorithm will do before actually updating its policy, so its controller, is 2000 steps. So we're probably just going to change that to see some improvement. So the only thing I'm going to do is redefine the model. And here we're going to say that we will update our agent every, I don't know, 120 steps or 256 steps, yeah, 200. Here we go, and here we can start the learning again. The only difference here is it will update its policy much sooner, and that's what we get here. Okay, so far so good. Any questions? So here we get some information about what is the mean length of the episode. So here we want the length to be as big as possible, because that would mean that the car is actually not crashing. Here it is the mean reward over 100 episodes. We also want that to be as high as possible, because we want our agent to solve the task. And then we get different information. So here, because we have the simulator, which is running 4 times faster, it will be, I think the FPS can go to 60 Hz, but because we are resetting, the FPS will be lower here. We have the number of iteration, so number of updates that we did to our policy, and then we get different information about the training. So, for instance, the current learning rate, current entropy of the policy. So it should be, so with 4 times simulation speed, it should be 80 FPS in the control loop, but we have a reset in the reset function. Actually, I think it's hard-coded to sleep for 1 second. So it will cap the FPS. We could change that, in fact, in the future. So while it's training, so this is nice, but this will be quite inefficient, especially both learning directly from Pixel and learning with PPO, those two combinations. So PPO is a model-free on-policy algorithm, which is quite sample inefficient. It is fast to run, but it's quite sample inefficient. And so instead of that, we're going to use an off-policy algorithm with a replay buffer. So if you go to stable baseline and you search, you go to RL algorithms. So in this table, the most interesting one are soft actor critic, TD3, TQC, which are all off-policy algorithms, so more sample efficient. And that's, in fact, I'm using TQC for the car. Okay. The other thing is, running something in the terminal is nice, but if we want to save checkpoint, if we want to save a lot of things, to save the best model, to save the hyperparameter we use to actually do the training, it's not very convenient. So the good news for you is, again, stable baseline got you covered. It's called the RL baseline zoo. You can also search for it for RL Zoo on Google. And the zoo is basically the training framework for stable baseline 3. It includes many things. So it includes a train script. It includes script for plotting the learning curves, and we're going to explore that also in the future. It includes script for hyperparameter tuning, automatic hyperparameter tuning, and other things like callbacks or wrappers. That's it. And the nice thing is once you have done that, you can directly take a look at the hyperparameters that you have used for one algorithm and change them here, and then it will save automatically all the information to reproduce the training. So what we're going to do next is actually clone that repo, so clone the RLZoo. So we're going to stop this training, because anyway, let's see how it's doing. It's probably not doing so well. Yeah, so it's still very early stages. It's not doing well. We're going to stop it here. Just close the environment probably before. Okay, so next things we're going to do. So we're going to the folder where we have our DonkeyCar. Is we are going to clone the RLZoo, because this is going to be the framework used to actually train the agent. And once we are in the RLZoo, we can again open it. No, we can open it. And if you want to, so this is the RL baseline zoo. Let me put it on the side. Does it make sense to remove the sleep 1 second on the reset to make the training faster? Yes, the sleep.1 second should be probably proportional to how fast is running the sim. So the sleep 1 second is also used because if you don't do that, there's a bug where the previous command sent to the simulator will be used as a first step, and so your car will start moving even though you did not send anything. And that's why there was a sleep also in the reset. But it would make sense to remove it otherwise. So with the RLZoo, you have all the gym environment included in it. And if you go to utils, import env, this is where you can import custom environment. And in fact, DonkeyCar is already included in it because I've been working with it. So you don't need to modify it, but for instance, if you're using another name, another package name, you can include your custom gym environment in there. Okay, and the good news for you is I already have a branch for the DonkeyCar simulator. It's called offline RL, so you can going to do git checkout fit / offline RL. So it's this branch has a little more features than that are more dedicated to the DonkeyCar. So especially in utils, yes. In utils, normally you have a teleop agent which allows to actually use the keyboard to record data or interact with the environment, but as a human. And the other things is in utils, in callbacks, if you go down, you have something called parallel training callback. So this is a special callback which allows, so it will allow your agent to continue interacting with the environment while in a separate thread there will be some training done. So in a separate thread there will be some gradient update. So it's a very experimental feature, but it actually does work most of the time. All right. So what's next? Next is we go to hyperparameter, and again, if you go to TQC, which is the off-policy algorithm we are already using, there's already the environment. Well, this is not the idea of the environment we want. So if I recall, the correct name is, if we go to init, no, the init above, what we want, the ID of the environment is called Donkey Mountain Car Track version 0, and this is what we are going to put here. All right. Next things is, what do we have in there? So in there we have many things. We can define all the wrappers we want around our environment. And here, actually, I was using a different version of the environment where I already pre-processed the image and output a vector using an autoencoder, and we could actually set up that. And then we have other wrapper, like a maximum number of time steps per trial, and the horizon wrapper. So this one is very also important. So if you want to your robot to have smooth action, and you want to penalize, for instance, jittery action, and you need to actually give the agent the previous time step and the previous action that was taken. Otherwise, you are breaking the Markov assumption and it won't work. So when you want to penalize continuity, so do a continuity cost, then this wrapper is super important. So it will give an history of the observation and action to the agent. So here we can remove. We don't need that. So we define the callback to do parallel training, and we will do the training, start a new thread every 200 time step, and then it will be synchronized. Then we define the maximum training budget, what type of policy is needed, and different arguments like the size, how many hidden layer do we have in our policy, how many critics do we have, when do we start, and things. So here we were just going to do a quick trial, so I'm going to comment out most of it. Here it's also for normalizing the observation and the reward. So I'm going to comment most of it, except the parallel training. I'm also going to change the policy because currently we didn't implement anything to pre-process the observation, so we need to use a CNN. The problem is with images, it will blow up your RAM quite quickly, so I'm going to change the buffer size to something quite small, so it doesn't blow up my RAM. And then what are we going to do? We're going to comment out the rest. I won't go into the details. So the main goal of today is just setting up things and getting them to run, even though it won't work completely. So once we have done that, what we can do directly is call the train function. So Python train, then we choose the algorithm. So the algorithm here is TQC. The environment is Donkey Mountain Track version 0. There's a special argument for parallel evaluation, and we're not going to use it, otherwise it will spawn another car, so we're going to set it to -1. And we can do things like save one model save checkpoints every 20,000 time steps, and this is how we save it. And do we have something else? And for instance, if we want to modify hyperparameter on the fly, I could directly change the learning rate here by passing it here as params. The same can be done for the environment keyword argument. So if you go back to our environment, it's not this one, it is this one. If you go back to the environment and take a look at the constructor, so here there's no much that you can pass. There's only the level and the configuration, but you could, I don't know, change the car name here, have something here that would change the name of the car which is displayed on top of it. And here you can also, for instance, change it directly using the RLZoo. So it needs a bit of escaping, but for instance here I could pass argument to my environment. Alright, enough talking. So here we're just going to launch some training, saving a checkpoint every 10,000 time step, using a CNN and a very small buffer size. Is there any question, remark, or anything that I missed? And if we look at the RAM, it will be quite. It's okay. It's 9 GB of RAM, but if you augment the buffer size, then it will also start blowing up the RAM. So it's something that you may not want. And same for GPU usage. You will see after 1000 time step, because it will do the parallel training, the GPU usage will be quite high because it's doing the parallel training in another thread. Okay, so I will just let the training go a bit. It won't learn anything useful because, again, we are learning directly from Pixel and this takes a lot of time. So instead, it was impossible to see the very end of the command line. Okay, so let me show the command line. So the command line is python train.py, then the algorithm, then the environment. Then we set the eval frequency to be -1, so because we don't want any evaluation environment, and we save a checkpoint every 20,000 time step. And for more configuration, in fact, everything is documented is in the README of the RLZoo. If you go in the README, and you can go here, you can see in the training agent, I think there's a lot of examples are now to pass different arguments, and that's what you see. Nope. So here, for instance, yeah, it's showing for the checkpoint, and if you go down in the example, there will be passing argument to the custom environment, which is probably, yeah, no, this is, it's in the README. It's a bit hidden. Yeah, here it is. So if you go to keyword argument, then you have the syntax for it. When you show how to provide the name of the car, it wasn't clear what was the command after 2000. Yeah, so if you want to provide the name of the car, I'm not going to launch the command, but so it will be a python train.py, and then you pass the environment keyword argument. Then you have the name of the keyword argument you want to change or to pass. And then you need to use two quotes, so double quotes and single quotes, because it needs some escaping. And here you can put a new name. Okay. So for the other viewers, yeah, don't hesitate to ask any question in the chat. Here, okay, this is something I actually wanted to talk about. Here, what's happening is the car is blocked and there's no termination condition. So it's my agent gets there after hitting the wall, no reset, did I miss something? No, exactly, that's something I wanted to talk about. This is an issue, I think, with the simulator and the contact registration. I think here it didn't detect any contact. So what we're going to do is also add a new termination condition, which is if we are below a certain speed for several time steps, then we're going to also say that we should reset the car. Okay. But before that, if you take a look at the logs in TQC, then you will have our experiment. You will have the last model. You will have the also this monitor will tell you how good it was for each episode. So it will allow us to plot things, and inside the folder, you will have two different things: the argument and the config that you pass to the agent. So for instance, the different hyperparameter that you change, or the argument that you passed to the training script, including, for instance, including the save frequency or the keyword argument that you may have changed. Everything will be saved by the zoo. So yeah, as you saw, it gets stuck. So what we're going to do right now is just fix that. So we need to open the environment, go to sim, go to here we go to the Unity sim handler. Oh, and bat is just a Rust replacement for cat. It's just the same thing. And if you go to the Unity handler, what we want to do is we have different things we want to do. We want to count how many steps we were below a certain speed, and if we are below that certain speed for too long, then we're going to reset the environment. So we're going to define end step low speed here, and we are going to also set up a minimum startup step, because at the very beginning of the episodes, anyway, the agent will be slow. So we need to also allow the agent to be slow at the very beginning, but that's all. So the first thing, and then we also need to specify a minimum speed below which we consider the agent to be stuck. And here I just set an arbitrary value of 1, but we can change that later. Okay, so once we have done that, if we need to also reset this number at every call to reset, so we need to go to reset, and here we'll set up that speed. Next is, where do we change the termination condition? I think it's called determine episode over. Determines episode over. So here we're going to just add a new condition, which is if the absolute value of the speed is below a certain value, which is our mean speed, then we're going to increment our counter of low speed. And if that counter is above a certain threshold, I don't know, during 3 seconds, if we are stuck, so 3 seconds is 60 time step, then we are also going to say that the episode is over. True. That's it. And as I told you, we also need to set up another things, that the actual number of steps in the current episode are above a certain threshold. And here we're going to wait, I don't know, for 3-4 seconds, 5 seconds before actually considering the agent to be too slow. And if it's not the case, then we're just going to if it's not the case, then we're just going to reset our counter. So the last thing we need to do is actually increment that counter of how many time step are we doing in our episode. Again, we need to define it in the init and in the reset. So in the reset, here we're going to reset it to 0, so number of time step in one episode. In the constructor to 0, and then it's called take action, if I recall. And here we're just going to increment the number of steps taken inside the environment. Just to recap what we have done, we just added a new condition for termination, which is if the absolute speed is below minimum speed, and we are after the start, so after allowing the car to actually speed up, then we're going to check how long have we been too slow, and if we are too slow too long, then we are going to set the episode over. And hello to my brother, so the pony from Moth. You can check out his Twitch channel. He has some very nice music in there and playing some games from time to time. So that's it, and that's the first tweak that we need to consider, and then we can restart the training. Here we go. So just reuse the same command. We save a checkpoint every 20,000 time step, and using same environment, but this time we have different termination conditions. so it should not get stuck. Okay, and while it's doing random things, if you have any question, it's also time to ask. And if you have any, where did you increase end steps? I increase it. So if you go to the environment and you go to take action, it's called take action. Here, every time I send an action to the simulator, then I will increment the number of steps taken. All right. Any other question? Now, so it's more or less everything I wanted to do today. I can go further, and we can do. We can try some, for instance, some pre-processing using a very simple edge detector, and do some training on that radius space. Or we can start taking a look at autoencoder. But I think I won't go further than more 30 minutes or 1 hour. So if you have any requests, that's the moment. What do you want to do, or what do you want to learn? Is there any hints how to install PyTorch? Yeah, so to install PyTorch, best is to go to PyTorch page, click on install, and then choose the configuration that you have. So I will highly recommend using Conda. And then if you are on Linux, Mac, or Windows, then you select what you want, and you have directly a command that you can copy paste in your terminal. If you're using pip, you can also just pip install it. What's the version I'm using? I'm using the latest version. So if I check out the version I'm using, well, it's not latest, but it's almost the latest, so 1.10 version. And RG is for rip grep. It's also a Rust replacement for grep. But yeah, that's a detail. So yeah, so for the 6-person viewing, please tell me what do you want to do next, or what do you want to try out. So here it's learning again directly from Pixel. It won't be super efficient. And what's missing currently is some pre-processing. What's also missing probably is penalizing change in the steering, too big a change in the steering. And in fact, if I recall, it will get stuck quickly and do the same thing again and again. Yeah. So what do you want to do next? Otherwise, I can also, as a probably include autoencoder would be great. I tried it already, one with your help of your repo. Okay. Anyone else want to take a look at the autoencoder? Then that would be next step. So I won't get too much into the detail then. Let's just stop. Yeah. So at least here it doesn't get stuck. So it won't get stuck because of the low speed, but it won't learn much even at four times the speed. So I'm just going to kill it, and it will again save everything. Even though I killed it, it saved everything, including the last model in this folder. So here, so far, we have been learning from Pixel. It's not very efficient. What kind of action noise do you use here? Yeah, good question. So there's different way of doing action noise. Currently, by default, it's a Gaussian action noise, but I would not recommend using that. And in fact, if you take a look at the hyperparameter, I'm using something called SDE for state-dependent exploration. It's something I've been working on, which is smoother exploration. And you can learn more if you search for GSDE, I think at call. It's called Smooth Exploration for Robotic Reinforcement Learning. It is included, in fact, also in Stable Base Entry, and this is much smoother for actually training it for real robots. And here in the simulator, it will also allow you to learn a smoother policy faster. If you want to have, in fact, a live example of it. I think it's called Furuta Pendulum. There was recently, if you search for me on Twitter, there was today a nice video of a French guy actually doing training a pendulum directly in the real world, and it shows the problem, actually the actual problem with using Gaussian noise. The main issue with using Gaussian noise with as exploration is that you will break your robot. You are just sending garbage to your actuators, and this exploration so is smoother and is dedicated for real robot training. So this is what I would be using, but as a first thing we can also deactivate it. That's okay. So next things I'm going to show, but very quickly, I'm not going to dig too much into the detail, is replacing the parts with some autoencoder. So doing some pre-processing for the agent, because if you pre-process the image, then the state space from which it needs to learn will be much smaller, and it will be much so faster to learn from. Again, I got you covered with a repo, and if you go on my profile, if GitHub allow me to actually see my profile, and you go in the repository and you search for, I think it's autoencoder. You search for DonkeyCar, you will end up with this repository. And in there, what do we have? We have a training code and augmentation code for training autoencoder. So autoencoder will just try to reconstruct the input image and compress the information into a smaller vector. And I'm doing some augmentation because I want also my encoder to be robust to different kind of noise, including if a car passes in front of me, I don't want to the representation to change, or if the light is changing, if there's some shadow, I don't want the representation to change. And that's what we have. And inside this repository, there's different things. There's two branches. One branch is for the car racing of Jim, and it has teleoperation. In fact, if you go inside and you go to record data, there's a small script that shows you how you could record data using Pygame. I don't have too much time, so I won't go too much into the detail. I will just show the basics on how to set that up. And the other thing it has is if you go to autoencoder and wrapper, it already has a nice wrapper that you can use with the RLZoo, and in fact we're going to use that right now. So again, next step for you would be to clone that repository. And in that repository, there's different things. So there's a training code for autoencoder. There's some testing code to actually see what was learned by your autoencoder. And we don't have too much time. So what I'm going to do, and that would be probably for the next video on how to train the autoencoder, I'm just going to use a pre-trained model. So, and show you how it looks like. It's in RL autoencoder here. So in the logs, I have got different model already ready. In the logs, I got also several datasets with different images. And I can show you, so let's see. Yeah. Here, what I'm going to show you is the autoencoder I use for the race on the DonkeyCar. Once you have trained one, how does it look like? And okay, no such file or directory. Oh yes, because yeah, it is not there. Oh yeah, this is not the correct one. It is in racing car. Or not. It should be. Anyway, I'm going to show you with destroy. Yes. And just pick one in there. Let's just pick that one. The goal is just to show you what it looked like and what we can do with it. And there's no dataset. Okay, dataset test probably. Yeah, I need to check that part because car racing version 0. Yeah. Okay, it has some issues because this I trained it for yeah, the car racing environment and not for the DonkeyCar. So we're going just to, yeah, okay. Yeah, it's the folder. Here we go. Okay, so today is apparently a wrong day to show you the autoencoder. I forgot to wait. Ah, okay, yeah. I use another repo for that. Okay, okay. Here we go. All right. So this is what you can get with the autoencoder. So on the left is the original image you get from the car. Then because most of the image is, well, part of the image is not relevant, I crop it. And then this is a reconstruction from the autoencoder, and then you can cycle through the image and see what is reconstructed or not. And see if the important information is actually saved or not. All right. I think that's it. And the other thing that you can do with this repo, so I'm using just slightly different repo, is turn on augmentation. And let me see just which common is it. It's augment. So here it will be, you will also have an additional view, which is the augmented view. So you will have some noise on the image, and then you will have the reconstructed image, even though there was some noise. And here, for instance, you have a big shadow, but even with a big shadow, you still have the main track, the main line, which is reconstructed. And this is the important thing to actually check once you have trained your autoencoder. And so I will just finish this live. So once you have trained, there's different things you need to do. First, you need to collect some data. You can do it by randomly driving through the environment and collecting the images. And once you have done that, you can use a training script. And once you have a training script, then you will end up with the autoencoder. And the last thing I want just to show you is, once you have the autoencoder, you can go, so here I'm just using the wrapper, so you can go to feature car racing and just copy paste most of it. In fact, most of it won't work because it uses a package which is not ready yet. And this is why I want to do a second live for that. And this wrapper, you can add it in the zoo. So if you go to the zoo, to utils and wrappers, here you can add it here. So this won't work because this package is not installed. And here you can also, using environment variables, you can set the path to your autoencoder. And what's going to happen with this wrapper, if you take a look at it, so I'm loading the autoencoder. I'm changing the observation space because I will use some pre-processing, and I'm changing the space, and and then I'm just going to encode the image using the autoencoder, and that's what I'm returning to the agent. And so once I've changed the observation space and I've just encoded during a reset and during the step the agent, I can directly, in fact, add that wrapper. If you go to the YAML file, you can go to wrapper here and comment, and you add an additional one, which is so utils.wrappers.autoencoder, and this will automatically load it when you call the training. Okay, so as I don't have much time for now, so I will finish this live by letting the agent train with the default reward and with the updated termination condition. So I've set it up before when I prepared this live, and I go to RLZoo, and here I just want to show what's different. Yeah, okay, let's see what's different. So this is more or less a sneak peek of what I plan to do in the next series of this video. So here I had the time to set up more than that, so I had to start to set up the autoencoder wrapper. I also added a speed wrapper, so the speed wrapper, we can quickly take a look at it. Because we are racing, knowing our current speed is very important. And what I added is in fact also another wrapper to include the speed inside the observation space. So what it is doing, it is just adding one dimension to the autoencoder, and is concatenating the autoencoder with the speed, and that's all what it is doing. Yes, and that's mostly it, and we don't need that in fact here, but that's okay. Okay. And once we have done that, I also added some continuity cost to make it smoother. And because I added some continuity cost, this is also what we're going to see in the next series. I gave an horizon to the agent. Because here everything is pre-processed, then I can use a MLP policy, and this will be also much faster to train. So I'm just going to launch the training. I'm going to reuse the same command I use here. So Python train. Here we go. And it won't work because I need to actually. Oh, it will probably. It won't work because I need to specify the autoencoder, I think. Yes, let me specify it. So this is here. I'm just going fast because this is the end of the training and of the live, and I just want to show you quickly a sneak peek of what you can do, just with almost out of the box gym. The main thing will be then actually will be actually all the pre-processing. So I'm going to let it run. Let me just okay. Okay. And I'm going to let it run, and then you can check in around 1 hour. It should have learned already something interesting. I will probably maybe put the terminal next to it so you can see the best reward. Let me see if I can add that. Capture off screen. Donkey. Where is it? Here we go. So there's a question: how long was training that won the race? So the model that won the race has been trained for, I think, 5 hours, but with simulation running 4 times the speed, so it's around 20 hours. But it was using a reward which you can use in the real world, so I'm not using the cross-track error. I was just optimizing for speed. But here, because it's using the cross-track error, it will learn much faster, and it will learn to go under 20 seconds in around 1 hour or 2 hours of training, which is represent 4 hours in real time. Your agent stops after n step equal 1. Is that possible? That may be possible, but that's weird. You need to check what termination condition happened. And also you need to check if it terminated because of the termination condition or because you're out of RAM or out of resource, because this can be quite demanding. So yeah, I wanted to add a terminal. Let me add that. Capture of, yes. We still cannot see it. Why? Okay. I don't know. I wanted to add. Can you show the hyperparameters again that was used? Yes. Let me share my whole screen then. Tick. Screen with cam. Yep. So if you go back, this is not this one. This is not this one. Should be this one. Yes. So I'm normalizing the autoencoder because the autoencoder is not always normalized. I'm using a time limit just in case it is stuck somewhere and I need to do something. I'm using autoencoder wrapper, so I'm actually pre-processing the data. You can use anything for pre-processing, but here I'm using autoencoder because it's easy to set up. I'm adding the speed as input, and then I'm penalizing also for continuity. And because I'm penalizing for continuity, I'm giving a history of wrapper. And the rest is mostly default. What is not default is using SDE, so using a smoother exploration, using a parallel training. The rest is mostly, and using a higher also learning rate. The rest is default, more or less. Okay. Yeah, I will probably then just let the screen like that and remove my cam. If I can remove it. Yes. Okay. Okay. So we can already see that the agent has started to take the very first corner, so it will take, again, longer to do more than that, but already in 5-10 minutes, you get the gist of it. Yeah, so in the last live coding session, yeah, I think there will be a full session about collecting data and training the autoencoder and actually checking that the autoencoder is doing something interesting. And in other live coding, we could also explore other ways to pre-process the data. For instance, directly extracting the line or doing other self-supervised learning for extracting features or using pre-trained encoders on other data. But yeah, today I don't have time because it's pretty, yeah, it will be pretty long, both to collect the data, both to train the autoencoder. But if you take a look at the repo, there's already some instruction on how to train the autoencoder once you have a data set. Okay, so I will. Oh, nice! It's already almost doing one full lap. And here, what you can see is that the main difference is we have pre-processed the data, so it's much easier to learn. We have the same action space, but we have observation space. So the observation space, what the agent receives as input, much smaller, so it's much easier to actually learn something. Okay, so let me try again. Okay, so thank you all for attending this session. I hope I will be off for 4 weeks, and then I will see when I will have some time to prepare everything, and be back for another session. So don't hesitate to motivate me to do it. You can find me in the Discord channel of the DonkeyCar. To send me a message again telling me, oh, actually you need to do the next session. So I will prepare it. And I really want to add the terminal to it. So thank you for watching. I will let the robot train for a while. And I will see. Okay. And of course, so thank you very much. If you have any more questions, just write them right now. I will be there for, I think, 5-10 minutes, because I'm trying to set up the terminal. And you can come back in, probably 1 hour, and you will see the robot, which should have learned at least to do several turns. And in 2 hours, it will be around 20 seconds. Where to find information about your model and RL? RL in general. So reinforcement learning, I recommend you to take a look at Stable Baseline 3 documentation. We have some resources to get started with it. One very good resource is called Spinning Up with Reinforcement Learning. And about my model, I'm not sure what model you want to talk about, but if you take a look at the Reinforcement Learning Baseline Zoo, then there will be already a lot in terms of recommended hyperparameters or what can be done with it. And find information about my next videos. So best probably for you is to follow me on Twitter. That's where I will post information about upcoming stream, or to also stay tuned inside the DonkeyCar Discord in the virtual racing team. I hope that answers your question. So for those who are still here, we have our first lap, which is 30 seconds, and it should go down quickly now.